Hello everyone and welcome to this video lecture.
Now let's solve the next two question paper, which are multiple choice questions based on interpolation and numerical integration. So let's firstly understand the concept of interpolation and numerical integration. Interpolation is the technique of estimating the value of the function for any intermediate value of the dependent variable. There are various methods in the interpolation. The first method here is the new is the Newton's forward interpolation formula. So let's understand the Newton's forward interpolation formula. We have taken a function y equal to fx, which takes the value as y0, y1, y2, and up to yn. And corresponding to this y0, we take the values as x0, and corresponding to y1, we take the values x0 plus h. And corresponding to y2, we take the value x0 plus 2h, and so on. And suppose we need to find the required function fx for x equal to x0 plus ph, where p is any real number. Let me just use the pen. For any real number p, we have defined e as ep of fx is equal to f of x plus ph, and then we have used the binomial theorem to expand the function x plus ph. And then finally we got the result of yp, where yp is given as y0 plus p times delta y0. And we here the delta is also known as the forward difference operator, which is defined as the forward value minus the initial value. That is, if we need to calculate delta 0, that would be equal to delta 0 would be equal to y1 minus y0. Similarly, if we need to calculate delta 1 would be equal to y2 minus y1. This is known as forward difference operator, or the delta operator. So the final result of the Newton forward interpolation formula is yp would be equal to y0 plus p times delta y0 plus p into p minus 1 divided by 2 factorial delta square y0 plus p into p minus 1 p minus 2 divided by 3 factorial and delta cube y0, and so on. So this is the required formula for the Newton's forward interpolation formula. And we need to keep in mind that the Newton's forward interpolation formula is only applicable for equally equally spaced interval. That is, the interval must be in a equal difference. The difference in between the two intervals must be the same. Then only the Newton's forward interpolation formula would be applicable. And we must keep the formula in mind as well. Now, the second interpolation formula is the Newton's backward interpolation formula, similar similar to the Newton's forward formula, which is used to calculate the value of the function at the initial stages. When we need to calculate the value of the function at the later part of the stages, we use the Newton's backward interpolation formula. So let understand it. Let the function y equal to fx takes the value y0, y1, y2. Similarly to the Newton forward formula, we take the values as y0, y1, y2, corresponding to the values of x0 to y0, x0 plus h to y1, x0 plus 2h to y2, and so on. And then we use the nabla operator over here. The nabla operator over here is known as the backward difference operator. It is the upper value minus the lower value. For example, when we need to calculate the nabla for var, we need to calculate backward nabla operator. For example, let's assume delta of 3. Delta of 3, we need to calculate it, so it would be equal to the upper value minus the lower value in this range. So that way we can calculate nabla 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 in this case. So the final result for the Newton's backward interpolation formula over here is yp is equal to yn plus p nabla yn plus p plus 1 divided by 2 factorial nabla square yn plus p plus 1 p plus 2 divided by 3 factorial nabla cube yn and so on. This is known as the Newton backward interpolation formula. The Newton backward interpolation formula is also applicable only when the difference between the two intervals are same. So now let's see the next interpolation, which is also known as the Lagrange's interpolation formula. The Lagrange's interpolation formula is applicable when the intervals are not same. That is, they have the difference between the two intervals is not same for each case. So in this case, when we take the function y equal to fx corresponding to it, the values of y0 and y0 x0 and y1 x1 and y2 x2 and similarly up to yn xn are being taken, then the value of the function at a unique interval would be fx is equal to x minus x1 x minus x2 x minus x3 and so on up to x minus xn divided by x0 minus x1 x0 minus x2 and up to so on up to x0 minus xn into y0. That is, we need to simply subtract the values over here with the values of x1 x2 up to xn and just leaving out the first value, that is x0, and in the denominator part we need to just subtract the values with x0 and then we need to just multiply it by the corresponding y0 part. Similarly, we need to calculate the values for each term by excluding the term in the in the numerator and including it in the denominator and multiplying it with its corresponding y value. So this is the Lagrange's interpolation formula, where Lagrange's interpolation formula always works only when the intervals are unequal. Similarly, we also have other method for unequal intervals, that is the Newton divided difference interpolation formula. In the Newton's divided difference formula, we use it for when the intervals are unequal. For suppose fx0, fx1, fx2 and fxn be the n plus 1 values of the function y equal to fx corresponding to the arguments x equal to x0, x1, x2 and up to xn. So f of x0, comma x1 can be given as fx1 minus fx0 upon x1 minus x0. We must keep this formula in mind. It is an important formula as well. So the f of x0 of comma x1 is equal to f of x1 minus f of x0 upon x1 minus x0. So this concludes the interpolation part. In the interpolation part, we have studied total of 4 interpolation techniques, which consist of when the intervals are equal and when the intervals are not equal. When the intervals are equal, we have studied the Newton forward interpolation technique and the Newton backward interpolation technique. And in the unequal part, we have studied about the Lagrange's interpolation, and the second one is the Newton divided interpolation. So now let's study about the topic of numerical integration. In the numeric integration, firstly, the important concept is the Newton Cotes quadrature formula. So firstly, let's know what do we mean by numerical integration. The process of evaluating a definite integral from a set of tabulated values of the integrated fx is called numerical integration. Which means that we have got a curve of y equal to fx and we need to calculate the area under this curve, y equal to fx. This method is known as numerical integration. This process, when applied to a function of single variable, is known as quadrature. Okay, when the variable here is specified, when the variable here is is single, then the term we use here is quadrature. So now let's study about the Newton Cotes quadrature formula. we need to find the integral of fx dx from the range a to b. So what we do over here is we divide the intervals into equal parts. As we can see, we have divided the y equal to fx curve into n parts, y0, y1, y2 up to yn over here, as you can see, and over here yn, and this is a trapezium. As you can see the here over here the y0 part, this is a trapezium, which the corresponding x values over here for y0 it's x0, for y1 it's x0 plus h, for y2 it's x0 plus 2h, and so on it goes up to yn, and for yn it's x0 plus nh. So now we have got the formula as integral of x0 to x0 plus nh. As we can see over here the lower part is x0 and the higher part over here is x0 plus nh. So over here we can say the lower range is x0 and x0 plus nh fx dx. Now what we do over here is we substitute the values over here and convert this x0 and x0 plus nh uh, to n. So we just simply put x equal to x0 plus rh. So we get dx is equal to hdr. So we just simply replace this dx by hdr. The h being constant comes out of the integral over here, and 0 to n f x0 plus rh dr remains over here. The 0 to the limits have been changed 0 to n as we put the values over here in x and x0 plus in the function x0 plus rh. So we when we put values x0 we get the value as 0, and when we put the value x0 plus nh over here we get the values as n. So the integral has been changed to h0 to n f x0 plus rh dr. Now we use the Newton forward interpolation formula which we have studied earlier to expand it. So it gives us the result as h0 to n y0 plus r delta y0 plus r minus 1 upon 2 factorial delta square y0 plus r into r minus 1 r minus 2 divided by 3 factorial delta cube y0 and so on, and multiplied by dr. So integrate on integration, we get it as nh multiplied by y0 plus n by 2 delta y0 plus n 2n minus 3 divided by 12 delta square y0 and n minus 2 whole squared by 24 delta cube y0 and so on. And now we put the values over here as n equal to 1, n equal to 2, n equal to 3, and so on. So when we put the values as n equal to 1, the trapezoidal rule comes into the play. When n equals to 1 and taking the curve through x0, y0 and x1, y1, we get the trapezoidal rule when n equals 1. So on calculating the values for x0 and y0, we get the value h2 upon y0 plus y1. As you can see over here, fx dx would turn to h into y y naught plus 1 by 2 delta y naught. So it becomes h by 2 y naught plus y1. Similarly, we get on in the next term we get as h multiplied by y1 plus half of delta y1. So we can write it as h by 2 y1 plus y2. And over here adding and then adding these integrals and summing up it, we get the formula of the trapezoidal rule, which is equal to h by 2 y0 plus yn plus 2 times y1 plus y2 and up to yn. This can also be remembered as the h by 2 is multiplied to the sum of the first and the last term, and two times the multiplication of all the remaining terms. This is known as the trapezoidal rule. Similarly, when we put n equal to in the Newton Cotes formula, we get the Simpson's one-third rule. The Simpson one-third rule is over here, as we have done in the trapezoidal rule on substituting x0, y0, x0, x1, y1, x2, y2. Similarly, over here as well, we take the curve through the points x0, y0, x1, y1, x2, y2, and calculate its value. And at the last, we add all these terms. So we get over here the value of the integral as h by 3 y0 plus yn 4 times y1 y3 y1 plus y3 up to yn minus 1 plus 2 times y2 plus y4 plus yn minus 2. You can also remember it as the sum h by 3 multiplied by the sum of the first and the last term, and 4 times the multiplication of odd terms. These are all the odd terms over here, and 2 times the multiplication of all the even terms left. As you can see over here, y2 plus y4 and up to yn minus 2, these are all the even terms, and y1 plus y3 and up to yn minus 1, these are the odd terms over here. So this is the Simpson's one-third rule. Simpson's one-third rule. Now the next one is the Simpson's 3 by 8 rule. In Simpson's 3 by 8 rule, we put the value of n equal to 3 and calculate the value of the integral. So the value of the integral comes out to be 3h by 8 into multiplication of yn plus y0. That means the sum of the first and the last terms. And over here, if you look at 2 into multiplication of y3 plus y6, these are all the multiples of 3. And as you can see over here, the remaining terms are being multiplied by 3. That is y1 plus y2 plus y4 plus y5. The remaining terms which are not the multiples of 6, multiples of 3 have been kept over here. So the formula turns out to be 3h upon 8 y0 plus yn, which is the first and the last term, 3 times multiplication of y1 plus y2 plus y4 and up to yn minus 1, which consist of the values which are not the multiples of 3, and 2 times all the numbers which are the multiples of 3. This is known as the Simpson's 3-8 rule. So now let's solve multiple choice questions based on the topic of interpolation and numerical integration. The first question is, which of the following interpolation technique is used to find the value of a function at a point lying outside the known data points? We need to find which of the following interpolation techniques gives the value of the function which lies outside the data point. As we know, the Newton forward and backward gives the value of the function at the starting near to the starting value, and the Newton backward gives the value at near to the end. And the Lagrange's interpolation gives when the intervals are uneven, which leaves us with the option C, the Newton divided difference interpolation. So we use this technique to calculate the value of the function lying outside the known data point. So the C option is correct over here. The second question is, which of the following is not a disadvantage, which means we need to find the advantage of the Newton's forward interpolation technique. The first option says over here is it cannot be used for large values of n, and it is true, as it is a disadvantage, as we cannot use Newton forward interpolation for large values of n, and it requires equally spaced data point. This is also a disadvantage, as we know that Newton forward interpolation only works on equally spaced data. So, so it is a disadvantage, as many a times the data given to us is not equally spaced. The third option is it is sensitive to errors in the data points. It is also a disadvantage over here. And it is the fourth option is it is computationally intensive. This is the correct option, which is the D. It is the computationally intensive. Computationally intensive means the number of data field requires to compute the value of the function is more over here, which gives us the value correctly and the error being reduced to a great extent. So the option D over here is correct. The Newton forward interpolation technique is computationally intensive, and which is not the disadvantage of it. Now let's move on to the third question. The third question says that which of the following interpolation technique is used to find the value of a function at points lying before the known data points. Lying before the known data point, lying before the known data points. in this we use the Newton backward interpolation, as we know that we use it to find the value of the function before the known data points over here. And in forward, we used to calculate the function value after the known data points over here. And Lagrange's interpolation is used when we need to calculate the value of the function when the interval is uneven. So the option C, the Newton backward interpolation, is the correct option. Now the fourth question says that which of the following interpolation technique uses a polynomial of degree n minus 1 to interpolate n data points. The option over here would be Lagrange's interpolation. As we have seen in the formula of the Lagrange's interpolation over uh, here, we can see that it goes from y0 to yn over here. So the number of polynomial required over here is n minus 1 to interpolate n data points. So the option D, that is the Lagrange's interpolation, is the correct option. Uh, Now let's move on to the question number 5. The question number 5 says that which of the following is not a disadvantage of Newton backward interpolation. The not and disadvantage of Newton backward interpolation is it cannot use the values of a large value of n, as well as it is completely intensive. So option D as well as option C, both can all be correct over here. Now, the sixth question says that which of the following interpolation technique is used to find the value of the function at points lying between the known data points? Lying between the known data points. Okay. So, in this, the first option is Newton forward interpolation, which is wrong, as we know that the Newton forward is used to calculate the value of the function at the starting, and the backward is used to calculate the function value before the function value, that is at the last. And Newton divided difference, which leaves us with the C option and the D option. The C option is Newton divided difference and the D option is Lagrange's interpolation. As we already know that Lagrange's is the correct option over here, as Newton divided difference interpolation is used to calculate the value outside the range function. So this is also the wrong option, which leaves us to D option, that is the Lagrange's interpolation. So the option D is the correct one. So the Lagrange's interpolation is used to calculate the value of the function lying between the data points. Now let's see the seventh question, which is the which of the following is the correct formula for Newton divided difference interpolation. As we have already seen Newton divided difference interpolation, we can just simply say the option A over here, which is f of x0 plus f of x0 comma x1 plus f of x0 comma x1 over here. This one, A option, is the correct. And now let's move on to the next question, which is question number 8, which says that which of the following is correct formula for the first divided difference in the Newton difference interpolation. As we all know, it's the starting term minus the previous term upon the x values initialized to the starting term and minus the previous term. So the option D over here, as we can see, f of xi is equal to f of xi minus f of xi minus 1 divided by xi minus xi minus 1. So the option D over here is correct, as we have already seen the formula for the divided difference, which is over here, as we can see f of x0 comma x1. So the value is f of x1 minus f of x0 divided by x1 minus x0, which over here over here is the D option. So the option D is correct. Now let's see the question number 9. The question number 9 says which of the basic difference between the Newton forward and the and backward interpolation method. So when we look over here, we see the question, we see the option number A, which says that Newton forward interpolation uses forward difference, where Newton backward interpolation uses the backward difference. As we have seen the Newton forward difference uses the delta operator, and the Newton backward interpolation uses the nabla operator. So this option A over here is correct. So this is the basic difference between Newton forward and Newton backward interpolation technique. So the option A over here is correct. Now let's see question number 10. Question number 10 says that in Newton's divided difference formula, what is the purpose of using higher order differences? The using of higher order differences just increases the accuracy of the interpolation. So the option A over here is correct. Now let's move on to question number 11, which says that which of the following interpolation method is not based on polynomial approximation. As we have already seen in Newton forward, we assume a polynomial y equal to fx, and then we use binomial approximation in this case as well. In Newton backward as well, assume a polynomial and use the binomial expansion to conclude the result. In Lagrange's interpolation, we take a polynomial of n degrees to conclude the result, which leaves us with divided difference interpolation. In this method, we do not use any polynomial approximation. So the option D over here is correct. So the option D, which is divided difference interpolation, is the correct answer over here, and rest all the options over here are wrong. So let's now move to question number 12. The question number 12 says that what is the difference between Newton divided difference interpolation and Lagrange's interpolation? Now, when we look at it over in Newton divided difference interpolation uses forward, whereas Lagrange's interpolation uses backward. This is wrong. Uh, as we all know that as we all know in Lagrange's interpolation, no backward difference is not required. The second option over here is Newton divided difference interpolation uses backward differences. This is wrong. It uses the forward differences. So this is also wrong. The C option is Newton divided difference interpolation uses divided differences, whereas Lagrange's interpolation uses polynomial interpolation. This is the correct option over here. So the C option is correct for Newton divided interpolation and Lagrange's interpolation. Now let's move on to question number 13. The question number of 13 says that which of the following interpolation method is more suitable for unevenly spaced data points? For unevenly spaced data points, we have two options over here, which is the divided difference and the Lagrange's. The Newton's forward and backward is used for equally spaced data points. So these options are wrong. So from the following divided difference and Lagrange's interpolation, the Lagrange's is the correct option, as it is more appropriate and suitable for unevenly spaced data points. So the option D is correct over here. Now the 14th question says that which of the following interpolation method is known as method of finite differences. The method of finite differences is known as for divided difference interpolation. So the option C is correct. Now let's move on to question number 15. What is the order of the polynomial used in Newton forward interpolation? The order of the polynomial used over here is n minus 1. As we look into the formula of Newton forward, as we can see over here, which is y0 plus y0 up to yn, so y up to n term y0 to n, which gives us the total of y of a polynomial of n minus 1 terms. So the option over here, option B, n minus 1 terms is the correct answer. So the order of the polynomial for Newton forward interpolation must be n minus 1. The next question number 16 is which of the following interpolation methods uses the concept of interpolation error? The Newton forward and backward do not use any of the error method, while the Lagrange's method uses it. So the option C, the Lagrange's interpolation, is the correct option. The 17th question is which of the following interpolation methods can be used to interpolate function with complex values? Complex for conclusion for calculating complex values, we use the Lagrange's interpolation as it is more suitable for the calculation. Newton forward and backward uses only is valid only for evenly spaced data points, so it doesn't work on the complex values. Similarly, the divided difference interpolation also doesn't work on complex values. So the Lagrange's interpolation is the correct answer, which is the option number D. And the question number 18 says, what is the drawback of using higher order differences in Newton divided difference interpolation? The drawback over here is a higher computational complexity. As we all know that the operations used in these methods are very conceptual, and the memory required for them to be computed is very high. So the computational complexity increases as the values are very large over here, and the operations can go up to many floating point digits, which increases the complexity of the overall program, and hence we do not promote to use the higher order differences in the Newton divided difference interpolation. So the option A, higher computational complexity, is the correct option over here. So the option A is correct. Now let's move on to question number 19, which says that what is the main difference between Newton-Cotes formula and Gaussian quadrature formula? The main difference between the Newton-Cotes formula and Gaussian quadrature formula is that Newton-Cotes uses equidistant point, whereas the Gaussian quadrature uses non-equidistant point. As we look into it, Newton-Cotes uses the equidistant points, whereas the Gaussian quadrature uses the non-equidistant, which is option number A. So the A option over here is correct. Now we move on to question number 20. The question number 20 says that which of the following is an example of Newton codes or numerical integration? As we have already seen, the Simpson's rules is the option over here. So option A and B both can be true. So the Simpson rules is just the answer. Both A and C. So the Simpson's rules is the example. So the D option, Simpson rules, is correct over here.